to do today, but there's a chance that I might be done today. So I'm going to just go back to what I was trying to do last time, and I know I messed it up last time, so I'm going to try again. And this time I had time to prepare, so I think it's going to be better this time around. So I was getting started in a discussion of stationary black holes. And the idea here is to attempt to come up with general properties of black holes, in this case stationary black holes. Later, probably this afternoon, I'll be talking about what happens in dynamical cases where we don't require the stationary conditions. But what I want to do here is to do a lot without having to write down a specific metric. So there's a lot of this stuff that we could do based on the details of the Kerr solution. We could derive all sorts of things based on Kerr. We could appeal to the uniqueness theorems that would say that for black holes in vacuum, it's really the Kerr solution that applies. But here I have an opportunity to do this without the details of the Kerr solution, and in fact it's easier if you don't have to write down the Kerr metric. You can do an awful lot without ever doing that. But also it opens up an opportunity because we could imagine our black hole to be surrounded by matter, in which case the Kerr solution would not be applicable, but we could still have a stationary black hole nevertheless, and all of the stuff that I'm going to be doing this morning will apply to this black hole that might be surrounded by matter. So we could do this. We can do stationary black holes outside of vacuum without assuming that it's a Kerr solution, but with still relying on what Hawking's proved in 1972. That's the stuff that I was telling you about last time that I'm going to just recap now. So that's the idea. The context is to try to generalize the discussion, but at the same time simplify the discussion by finding other ways of deriving things that don't rely on the Kerr solution. So just to clarify a couple of terms, stationary in GR is always used to mean, well, in the simplistic formulation, it really means that your metric doesn't depend on time, and whatever matter fields you might have in the space-time also don't depend on time. So there's no t dependence in a suitable coordinate system, but of course we know that a fancier way, a more geometrical way of expressing this is to say that we have a Killing vector. We have the existence of a time-like Killing vector. So an example of a stationary spacetime would be something like Schwarzschild, where you have nothing that depends on time. But the Kerr spacetime is also an example of a stationary spacetime because while it also doesn't depend on time. A static spacetime is a particular case of a stationary spacetime where you also demand that not only is the metric time independent, but the metric also has to be time reversal invariance. So we have time reversal invariance. And the fancier version of this is to say that the Killing vector that we had to begin with will be hypersurface orthogonal. So that's in the sense of Frobenius, where I don't care that the Killing vector is not associated with the congruence of geodesics. We have the more general version of the Frobenius theorem that tells me that the Killing vector will be hypersurface orthogonal if there's a mathematical condition associated with that we remember from a while back. But that's an extra condition on the Killing vector that makes the spacetime that was stationary static. And the main distinction here is that, well, would occur for Kerr. So Kerr is a stationary spacetime, but it's not static because the time-like Killing vector for Kerr is not hypersurface orthogonal. The physical way of seeing this is that the Kerr solution is not time reversal invariance, because if you switch the arrow of time, if you send it backwards, a rotation that used to proceed this way will now proceed in the opposite direction under time reversal. And that means that, well, you don't have this time reversal invariance. You have a change of sign in the angular momentum under time reversal invariance. So Kerr is stationary, but Kerr is not static. Schwarzschild is both stationary and static, right? So it really has to do with the properties of the killing vector existence and then whether or not there's hypersurface orthogonal. So those are just the technical definitions for these terms, and it's important to know them because that's terminology I'm going to be using right now. So the theorem by Hawking states that a stationary black hole is either static or axially symmetric. So if it's static, that means that it's non-rotating, and that means that we have, at least one time-like killing vector. That's the only one we care about. But if it's rotating and it's not static, then it's going to be axisymmetric, which means that we're going to have two killing vectors at our disposal. The time-like killing vector that the stationary property guarantees, and then the rotational killing vector that the axisymmetric property guarantees. So we have T alpha, as I told you last time, which is going to be the time-like killing vector. Time-like in quotation marks because it's not going to be time-like everywhere. We're going to have phi alpha, which is going to be the rotational killing vector. And we're going to have a linear combination of the two that will be null on the event horizon. So the theorem requires that we are talking about black holes, therefore we need an event horizon. The event horizon will be where a suitable combination of those killing vectors will be null. So Xi alpha is going to be some linear combination of killing vectors, which is itself a killing vector, and that's going to be null on the event horizon. So that's basically the content of the theorem. Omega h is, is pretty much, as a result of this equation, is the rotational velocity, the angular velocity of the event horizon. So as you follow the generators of the event horizon, you see that they're rotating because there's a component of its tangent vector along the rotational direction, and the rate at which they're rotating around the horizon is given by omega h. If omega h is 0, then it's not rotating. This killing vector becomes irrelevant, and we find that the killing vector that's tangent to the event horizon is the time-like killing vector. And that's the case we encountered in Schwarzschild. So in the non-rotating case, when the black hole is non-rotating, okay, so pretty much all of this I stated before. I should really state that omega h is constant, because it's only when you have, a superposition with constant coefficients that this combination here will end up being a killing vector. So that's an important condition. All right? So starting from this, the point is that we can do an awful lot. We can derive all sorts of things just from this, this set of statements. So let's get going with that. So the vector being null on the event horizon means two things, right? So we're going to have a null surface. So if I define, as I did last time, if I define v squared, and that's not the Kruskal coordinate, it's just a different definition for v. If I define v squared to be the norm of the Xi killing vector, then the statement is that this quantity is going to be 0 on the event horizon, and what I have, of course, is a null hypersurface. And I have a null hypersurface that's, that has all the usual properties of null hypersurfaces. So they're going to be generated by, traced by null generators. The null generators, of course, will have Xi as their tangent vectors, And this vector will satisfy the geodesic equation on the horizon. So we have a null hypersurface traced by null generators to which Xi alpha is tangent. So that's the usual situation, and we also have the usual situation that Xi is going to be both normal and tangent to that null surface. So Xi alpha is also normal to the event horizon in the usual null sense. So all of that comes from the null condition, comes as a consequence of the theorem. And one consequence of this is that where, this killing vector over here, which is defined everywhere in space-time, so while this killing vector would not satisfy the geodesic equation anywhere else, it will satisfy the geodesic equation on the event horizon. So it's only on the event horizon that it turns out to be tangent to null geodesics that will trace that hypersurface. Anywhere else, that vector is going to be time-like, or space-like, depending on what it wants to be. It's going to be tangent to curves, but those curves are not going to be geodesics. There's no reason for them to be. So Xi, a consequence of this is that Xi alpha satisfies the geodesic equation on the event horizon only. So I'm going to introduce a parameter along those null geodesics. I'm going to call it V. So that's going to be analogous to the Eddington-Filkenstein coordinate that we used before. And that would be the sort of same parameterization that I used in the Schwarzschild case. That's a well-defined coordinate. So if we're using V as a parameter, then what we're led to is the statement that Xi will satisfy this equation on the event horizon with possibly a non-zero right-hand side, because I can't assume necessarily that V would be an affine parameter. And in fact, for Schwarzschild, we already found out that V was not an affine parameter. We had to introduce a kappa term there, and kappa had this interpretation of being a surface gravity, right? So here, the bottom line is that we have to come up with this equation. This equation has to be a consequence of all this. And it basically just follows from the existence of an event horizon on which Xi happens to be null. So, so the existence of the event horizon is basically the statement that this killing vector will end up being null on that null surface. And that property by itself guarantees that this equation has to be satisfied. Now, I can prove that, but I think we have enough experience now with null hypersurfaces to know that, the very fact that we're dealing with a null surface guarantees that this null surface will be traced by null generators, and those null generators will be geodesics of that surface, geodesics of spacetime, and therefore the tangent vector to those geodesics will have to satisfy the geodesic equation. Sometimes the geodesic equation might be written with a zero right-hand side if V turned out to be an affine parameter, but in the general case, as we saw in Schwarzschild, there's no reason to presume that V would be an affine parameter. All right, I'll just fill in a couple of steps just to just to flesh this out a little bit. But do you have a question?
Just clarify, two V's are not the same.
That's little v, yeah, sorry. That's big V. I should have called it something else. I'll call it something else. I'll call it phi. Yeah, so that's my usual notation anyway, so I don't see why I deviated from that. So V is is whatever parameter. So I'm given a vector. The vector will be tangent to curves. The vector will provide its choice of normalization. I just call it V. So so that's that's where it comes from. So a displacement on a generator will be described by the statement that the change in coordinates is going to be proportional to xi and proportional to the increment in the parameter. So that's what it means. Okay. So let me just prove this because it follows very quickly. So the proof is that, well, we have the statement that phi is equal to 0 on the event horizon. And if we want to construct the normal vector to the horizon, we just take a gradient of this. So the gradient of this is going to be the normal to the event horizon. And the normal, as usual, is also going to be tangent. So that vector has to be aligned with the killing vector. So I'm just going to write this proportionality condition between this vector and this vector in terms of some proportionality constant, and I'll call it kappa, and I can consider this to be the definition of kappa, right? So this defines kappa. And again, what I'm saying here is that the normal vector to the horizon has to be aligned with this vector, which we know is normal to the horizon in the sense of being at once normal and tangent, and therefore we have to have proportionality between this vector and this vector, and the proportionality constant, I just call it kappa. And what I want to prove is that starting from here, I can get back to this equation with the same kappa. All right. So this defines kappa. So what we can do now is to go back to the definition of phi. This guy here is defined as the norm of the killing vector. So we can differentiate this. I can replace this by a covariant derivative. Then the metric is transparent to this. So we get twice xi mu differentiated with respect to alpha times xi mu, because I've used the metric to lower the index on the second vector. So I get two contributions, so I get a factor of 2. I can use the killing equation, because remember, we're talking about a killing vector here. So one property that this vector has is to satisfy the killing equation. So I can always flip the order of the indices over here. So I get -2 the vector differentiated, but with the flipped order. And what I find is that the left-hand side evaluates to this, the right-hand side is equal to that. And let's see, I seem to have a discrepancy in sign here. Okay, well, let me define kappa this way. And therefore, I have the statement that xi alpha mu, xi mu is going to be equal to kappa xi alpha. All right. So I see lots of puzzled looks. Is there something that's not clear here? I'm going to take off from here, so if there's anything not clear, I would like to clear it up right now. No? Okay, you're all happy with that? Yep.
When we first did the geodesic equation, the kappa there was usually like the partial derivative of the sum of the
yeah, so it could come from there, but it's basically just what you get for the general statement of the geodesic equation. So whenever you're not dealing with an affine parameter, then you get a kappa term, and yeah, kappa can be defined in terms of this, this total derivative of the Lagrangian function for that, for the action, for the geodesic motion. But that's sort of not really relevant for this discussion. I mean, yeah, you can relate it to that, but it's not terribly useful. Yeah, well, it's not arbitrary. It's also, you could also say, okay, this can be related to a Lagrangian derivative, but it's just not very, it's not very relevant for what we're talking about here. Okay. Any other questions? Okay, so basically, again, so the chain in the argument here is that we have the existence of this killing vector on the event horizon. The event horizon is a null surface, so this vector has to be, is going to be null. It will then be used to define the event horizon, and it's going to be guaranteed to be tangent to null geodesics. And that's the equation that tells us that, sure enough, if you have a null surface, that's the, the derivation here is that if we do have a null surface, then by virtue of this condition that it's a null surface, and by virtue of appealing to Killing's equation to simplify things, then we end up with this equation over here. All right, so that's the statement number one, that we have an event horizon, that we have a Killing vector that's tangent to it, and that we have a network, we have a congruence of null generators on the event horizon, and all the stuff that we've seen before, but now in the context of black holes. So you have a question?
Probably stupid, but did the event horizon have two normal directions? Or is this horizon a three-dimensional object in our four-dimensional space now?
Yeah, it's a full three-dimensional null hypersurface in a four-dimensional manifold.
Okay.
Right, so it has the direction that's, that's along the generators. And it has the directions also that's across generators, so that's something we'll talk about a little bit later.
Yeah, so I was because it's null direction, it must have there's like usually two.
Oh yeah, and then there's going to be another null vector that's going to cut across the surface, and we'll talk about that later as well. So that would be the vector n that would be pointing across the surface, not into the surface. Okay. And that would complete the basis, the vector basis on the event horizon. So that I'll introduce a little bit later. Okay, so we're all good here? All right. So kappa, as defined here, either here or here, kappa is going to be, is going to be, well, we're going to show it to be constant on the event horizon. So that's not proved yet, but it will turn out that so kappa will be shown to be constant on the event horizon, and it's known as the surface gravity of the black hole. Basically, we give it the name surface gravity because in the case of Schwarzschild, as we calculated it, it was given by basically m over r squared, where r was 2m, so we got the 1 over 4m squared, 1 over 4m. So it had the interpretation of the surface gravity as if you were to use the Newtonian expression for surface gravity and evaluated that on the event horizon. So by analogy with this, or we just give this quantity the name surface gravity. In which sense it actually does represent surface gravity? Well, it's not so clear. There's a limiting procedure. There's a sort of, limiting procedure by which you can sort of understand this quantity as a surface gravity, but the interpretation, at least to my judgment, is not that compelling. But certainly the name is stuck. But we can just think of this as being, well, a constant coefficient here in that we stuck into the geodesic equation. The fact that it's constant on the event horizon is highly non-trivial. When you derive the general form for the geodesic equation, there's certainly no requirement that kappa be constant on each generator, but that will turn out to be true. And there's certainly no requirement that it should be the same constant as you go from one generator to another, to another, to another. That it happens to be the same constant for all the generators on the full event horizon is something that is a rather remarkable result that follows from what we're going to be doing. And it's known as the zeroth law of Blackwell mechanics. So part of what I want to do this morning is to derive this result. It's a very, very pretty result, but very non-trivial and not obvious at all. Okay. So let me extract a couple of more consequences from the stationary condition. We can write down Raychaudhuri's equation. and say something useful about that. So here I'm going to use the generalized version of Ray-Chowdhury's equation, the one that you derived a while back for a homework assignment, one that, the one that doesn't require the parameter to be affine on the congruence. So we're going to use V instead of an affine parameter. So the generalized form of the Ray-Chowdhury's equation had this extra term in it involving the kappa quantity that appears in the geodesic equation. So that's the form I want to use, because the form we originally talked about in the context of congruences was restricted to affine parameterization, which doesn't apply here. So that's, so there's an extra term in the Ray-Chowdhury equation that would occur in general. But here, because I'm talking about a null surface, I know that my congruence of null generators will be hypersurface orthogonal. So I know that there's no rotation involved for this congruence. Hi, Steve. So I'm going to throw this out. And the other thing I'm going to do, there's no 8 pi here. What I was going to do is to relate this to the Einstein field equations and rewrite this in terms of the energy momentum tensor. So the form of Ray-Chowdhury's equation I want to use here is the one that says that d theta dv is equal to kappa theta minus a half theta squared minus sigma alpha minus 8 pi t alpha beta c alpha c beta. So that's the form of Ray-Chowdhury's equation that would apply to any event horizon. So there's no restriction here at this stage. The only thing that we did from the completely general case is to say that the rotation tensor is 0, and that's appropriate because we are talking about a null surface. If I'm talking about a stationary horizon, I can put all sorts of things to 0. A stationary horizon means that the expansion of the null congruence on the horizon will be 0. Stationary means that there's no expansion, and it also means that there's no rate of change of that expansion. So for a stationary horizon, we can set theta equal to 0. We can set the rate of change of the expansion to 0. If my horizon is expanding, I don't have a stationary situation. And as we're going to see, the second law of black hole mechanics forbids my horizon from shrinking. So here we consider basically the marginal case where we have a stationary horizon and therefore 0 expansion. If we have that, then we can kill this, we can kill that, we can kill this, and we have to conclude that the sum of those two terms is equal to 0. So for a stationary horizon, I must have this. Now, if I don't say any more than that, I would have to look at the sum as a whole. But if I impose the null energy condition, then I can say that each term is going to be 0. So with the null energy condition, I can say that this term by itself has to be greater than or equal to 0. The other term is guaranteed to be non-negative all by itself because sigma is a spatial tensor. It has no timeline component, and the square of a spatial tensor has to be non-negative. So if I impose the null energy condition, which I will here, I have a sum of two terms that cannot be negative being 0, and that means that each term in the sum must be 0 all by itself. And if the square of sigma is 0, sigma being a positive definite tensor, it means that sigma by itself has to be 0. So a stationary horizon has no shear, and it cannot have an energy flux across it. This component of the energy tensor describes how much energy is crossing the event horizon, and that amount must be 0. And that sort of makes sense because, if there's a flux of energy across the horizon, you can expect that the generators will respond to it. They will focus as a result to that, and that will violate the stationarity condition. So in order to maintain this stationary condition, in order to have a stationary black hole, we have to make sure that there's no energy flux across the horizon. There can be energy straddling the horizon, like we have for Reisner and Nordstrom. We had electrostatic energy. But if you calculate the energy momentum tensor associated with the electric field associated with the Reisner and Nordstrom solution, you'll find that this component vanishes. So, conclusion for stationary horizon, under the assumption of the null energy condition, we have that there's no shear and there's no flux of energy across the horizon. So this is a no flux condition. So a stationary horizon is pretty simple as far as the congruence is concerned. It's a no shear, no rotation, no expansion congruence. And in order to make that compatible with Ray-Chowdhury's equation, it has to be true that there's no focusing going on. And the no focusing condition basically amounts to saying that there will be no flux of energy across the horizon. If there is flux of energy, well, the horizon will have to respond. It will grow, in fact, in response to this. And that's something we'll talk about later today. All right? So lots of very beautiful statements that can be made without ever writing down a metric. And that's what I like about this approach, is that all of this follows just from very simple geometrical ideas and the existence of a killing vector. So it's very powerful. All right, any questions about that? I see a discussion at the back. Can I help?
I'm just trying to see why each component of the shear had to be 0.
Right. So so when you have a positive norm, if the norm of a tensor under a positive, so if a positive norm tensor is 0, then each component has to be 0. So if the norm of a vector is 0 under a positive norm, then each component of the vector has to be 0. It has to be the 0 vector. If the norm is non-positive, like we typically have in space-time, then you can't conclude anything like this. But here the key is that sigma is a spatial tensor. We know that it doesn't have any time-like entry, or null entries in this case, and therefore positivity of the, so this here is guaranteed to be a non-negative, and it can only be 0, and that's the point. So I want, so I have a sum of two non-negative things and ending up being 0. That can only happen if both are individually 0. And if this is 0 all by itself, then that means that sigma has to be the 0, has to be a 0 tensor. There are no negative, so the norm being positive here, effectively positive, because we're dealing with a purely transverse tensor. Remember that we did all this stuff with null congruences where the shear and everything was decomposed along the transverse directions. You don't? Yeah. So all those tensors were purely transverse tensors, and therefore they were purely spatial tensors. All right? Yep.
I can't remember why our conference is null. It must be hypersurface orthogonal. I mean, if I think of like a curve black hole, I would think that the omega tensor would be non-zero for that one.
Okay. No, right. No. So the interpretation of omega is a little bit delicate. I mean, sometimes it's 0 when you expect it. Sometimes it's non-zero when you don't expect it, and it's kind of strange. So, but let's be careful about this. So when you have a null hypersurface, the congruence on it will be hypersurface orthogonal. Any null congruence in Kerr, or a random null congruence in Kerr, doesn't have to be non-rotating. Certainly not. Mm-hmm. So there's something called the principal null congruence of the Kerr black hole that certainly has a non-vanishing rotation. It's just that, that's a theorem that we talked about before. If you have a null surface, or if you have a congruence that's hypersurface, well, if you have a hypersurface that's orthogonal, if you have a congruence that's hypersurface orthogonal in the sense of being, surface tracing in the null case, then Frobenius theorem tells you that that the rotation tensor has to vanish. So the rotation, the rotation tensor. I mean, it's a little bit of a funny thing because it's not just a rotation; it's actually a space-time rotation. So it's a relative boost between two members of the congruence, and this is not necessarily associated with a rotation. So you could have a rigidly rotating congruence that has no relative rotation, and this measures the relative rotation between members. So yeah, sometimes it's a little bit tricky to wrap around the language around what this thing really describes. All right. Okay. Can I proceed from here? Okay. So basically, those are just results you can derive right away from the property that a black hole is stationary. The one I want to turn to now, and the one that's really amazing when you think about this, is the notion that the surface gravity parameter should be constant, not just as you follow each generator, but also as you jump from generator to generator. You'll have the same constant describing the geodesic motion of all the generators on the event horizon. So that's something that we saw was the case in Schwarzschild. In Schwarzschild, it was sort of built in and guaranteed because the horizon was spherically symmetric. So if you have a horizon that's spherically symmetric, well, there's really no distinction between any generator because each generator corresponds to, a preceding generator. It just corresponds to a rotation, right? So you can start from one generator and you generate all of them by a spherically symmetric translation. So each generator basically ends up being completely equivalent to any other generator. But if you think about this for Kerr, well, Kerr is not spherically symmetric. Kerr is very much deformed. It has a bulging going on at the equator. It has a flattening of the poles. So there's a latitude-dependent shape to the event horizon. But nevertheless, the surface gravity parameter is going to be the same on each generator. So it's a one constant. It's uniform on the event horizon. And that's highly non-trivial. That's something that was discovered pretty much by accident in the case of the Kerr solution. But it turns out that there's a very deep reason why this result is true. And what I want to do now is to spend quite a bit of time, because it's a non-trivial result to derive, going through the proof of what's known as the zeroth law of black hole mechanics. And here I'll give you a version of the proof that was pretty much the original version as given by Barden, Carter, and Hawking in their early 70s paper. It's streamlined, it's adapted to the notation I like to use, but it's pretty much straight what they produced from the 70s. Yep.
Is psi defined other than just being velocity vector for generator of the event horizon?
It's defined, so you probably missed the early portion of this board here. So first, it's defined as a Killing vector. So it's defined globally in space-time as a Killing vector. But it happens to be the Killing vector that is null on the event horizon, that goes null on the event horizon. And as such, then it acquires the definition as being tangent to the null generators. Yeah, but the Killing property certainly is very important, and we're going to use it in the rest of the discussion. Other questions? Okay, let's get going. So I want to prove and, state the zeroth law. And the zeroth law says that for stationary black holes, kappa is uniform on the event horizon. It's a single constant valid for all the generators. We call it the zeroth law because, as we're going to keep talking today, of course, and you're familiar with this already, we are going to have a bunch of laws that describe the behavior of black holes. That's the zeroth one. We're going to have a first one that describes how black holes change under physical processes. We're going to have a second law that says how the black hole always increases in area. And in the 70s, it was noted by these guys, Carter, Bardeen, and Hawking, that there was a really amazing analogy between the laws of black hole mechanics and the laws of thermodynamics. And it's only after Hawking discovered the Hawking process that this analogy was basically, that was understood to be more than just a formal correspondence between things, but it became understood that, well, when we talk about the laws of black hole mechanics, we're really talking about a specific version of the laws of thermodynamics as they apply to black holes. So the analogy is amazing on a formal level, but it's also very deep-rooted in fundamental physics, because when you talk about thermodynamics and black holes, you're talking about gravity, you're talking about quantum mechanics, you're talking about all of those things together, and we're still trying to understand all of this today. We still really don't have a very good answer for what the statistical entropy of a black hole is supposed to mean and all that. Okay, so how do we prove this? Well, it turns out to be surprisingly involved to prove this. So I'm going to spend some time doing that, but I find the whole method very appealing, and it's basically something we can build from what we know. So all the tools and all the techniques that we've introduced so far will be put to use here, and we just have to be patient and just go through the calculation and do it systematically. So what we're going to do is do the usual thing. So we have an event horizon, which is for us just a null surface. We have a bunch of generators on that surface. We're going to introduce, as we have, a parameter along the geodesics, which we already have, that's V. We're going to introduce generator labels that are going to be constant on each generator. That's going to be my angular coordinates theta A. We've seen all of this before. We're going to introduce a basis of vectors on the event horizon that will include, so this is each generator is characterized by coordinate labels, theta 2 and theta 3 being constant. We have V running on each generator. We have a tangent vector on each generator, which is C. I used to call it K. Now we're going to call it C to remind ourselves that it's a killing vector. We have transverse vectors on the event horizon that will be pointing from generator to generator at constant values of V. So we have all of this, and on top of that, we're going to have, now we're reintroducing that additional null vector, the auxiliary null vector. That's going to be the other null direction that points away from the event horizon as opposed to pointing tangent to the event horizon. So we're going to have intrinsic coordinates on the null surface as we have had before. We're going to have a vector basis. That's going to be our usual tetrad of two null vectors and two spatial vectors. We're going to have a completeness relation, as we have had before, that will allow us to decompose, sorry, it's not K, it's C. We're going to have a completeness relation that will allow us to decompose the metric on the event horizon in a convenient way. So the tangent vector is, of course, K. C is going to be defined to be partial derivatives keeping, moving along the generators, so we keep the generator labels fixed. The transverse vectors are going to be partial derivatives across generators, keeping V fixed. And sigma is going to be the induced metric on the event horizon, given by all the inner products between the tangent vectors. So all of this is familiar. All of this basically is given to us from just the fact that the event horizon is a null surface. What I want to do to prove the theorem, I need to prove two things. I need to prove that kappa doesn't change if I move along a single generator. I need to prove this. That will be the easy one to prove because it follows pretty much directly from the killing symmetry. Nothing changes as you move along the killing vector, including kappa. So that's not the hard part. And that's not even the surprising part because the killing symmetry very much implies that as you move along one generator, kappa cannot change because you're moving along the orbit of a killing vector, and nothing can change as you move along that direction. So this one will be very easy to prove. The surprising one is the statement that says that as you move across generators, kappa also doesn't change. That's the surprising part. That has nothing to do with killing symmetries. We're aware that there's going to be a rotational killing vector on the event horizon, so to have invariance under that direction would not be hard to prove and would not be surprising. But the statement here is that you can move in any direction on the event horizon and never notice a change in kappa. That's the remarkable part, and that's the hard part to prove. So we're going to need to prove this, and we're going to need to prove this, and if we prove both, then we have that statement. All right? So we're going to do some groundwork in order to be able to access this. The derivation of this will rely a lot on the killing equation. So we'll have to import the killing equation, in many different places. And the killing equation will involve this quantity right here. In fact, many things will involve this quantity right here, including the statement of the geodesic equation and all of this. So the first thing that I want to do is to basically write down an expression for what this has to be on the event horizon. So how do we proceed with this? Well, the way we proceed with this is that, well, we recognize that this is going to be a tensor. And a tensor can be decomposed into a vectorial basis on the horizon. And all we have to do then is to work out what each coefficient has to be. So what I'm going to do is to introduce the most general tensorial decomposition we can have given our vectorial basis. And we're going to start working to identify what each term is in that expansion. We're going to import all the properties we know this has, including the killing property, and we'll end up with something that will be useful and useful for our calculation. So what I mean by that is that here's a tensor, and here's a vectorial basis. I can expand any tensor in this vectorial basis by just including enough terms in the expansion. So that's what I'm going to write down next. But you have a question first?
That n vector, it's chosen with a specific normalization.
Yes, I forgot to indicate this. So n is null by definition, but it's also normalized such that it's going to satisfy this equation. Yeah. So that is put in so that the completeness relation takes this form over here. So you can always choose that. And of course, n is also orthogonal to all the transverse vectors. Okay, so let me just write it down. I think it will be obvious what I mean. So this vector can have a component purely in the direction of xi. This tensor can also have components along xi and n. And it can also have components along xi and the transverse vectors. This vector can also have a component along n and xi. It can also have components along n and n. And it can also have components along n and the transverse vectors. Sorry, I didn't quite write it properly, like that. And then we keep going, so we can have components along the transverse vectors and along xi. It can have components along the transverse vectors and n. Sorry. And it can have components purely in the transverse directions. So at this stage, I'm just saying I have whatever tensor, and that tensor can always be written in a decomposition like this, where you just insert as many terms as you need in the decomposition. And here we have, well, basically the whole bunch. And at this stage, I haven't incorporated any properties that I know that this tensor satisfies. This is just the most general thing you can write down. So this is a general decomposition. And what I'm going to do now is to start importing all those conditions that we know that this tensor satisfies, and we're going to start killing off terms, or identifying terms in terms of things we already know about, including the surface gravity. Yep.
What's the double subscripted E?
It's those tangent vectors over here.
Oh, there.
Yep. Yep. So those are the vectors that are pointing across generators in a purely transverse directions on the congruence. Okay, so let's do it. So it's going to take a little while to go through all of this. So the first property I want to introduce is, is to recall that the vector is null on the horizon. And that imposes that 0, that the norm, the norm of the vector, if I differentiate along the congruence, that has to be 0. So this quantity here is 0 everywhere on the horizon, and it stays 0 as I move along a generator. So that means that this derivative is guaranteed to be 0. Is that clear? So when I calculate this, I get twice the same contribution. So I get that. We recognize this, but that will become relevant later. The other thing I can do is to differentiate the null condition along the transverse directions, because it's also true that as I move across generators, the null vector stays null, the killing vector stays null as I go from generator to generator. So this derivative also is well defined and will be 0. And this gives me twice C alpha differentiated in the direction of my transverse vector. Okay. So let's calculate this combination over here. So according to the general decomposition, if I multiply through by xi, I'm going to kill all of those terms. When I multiply by xi, I'm going to generate minus 1s from all 3 terms over here. And I'm going to get zeros from all of those because xi is orthogonal to E. Right? So when I calculate this, I get minus D C beta. I get minus E N beta. And I get minus FA E A beta. All right. Now, let me multiply again by xi. The result has to be 0. When I multiply again by xi to consider this quantity over here, I'm going to kill that. This will become plus E, and this will become 0. And what do we learn from this? Well, we learned that E is equal to 0. So one term in my expansion was not required. So we're going to kill many more. If I calculate this guy, I'll use a different index here just to distinguish from the A that was here, then that means that I multiply this equation through by a transverse vector. I'm going to get minus FA from here, and EC multiplying EA will give me an induced metric. And if that has to be 0, and we know that the induced metric itself is not 0, then that tells me that FA by itself has to be 0. So this term also goes away. All right? So we just keep going like this. So this was one property that C has to satisfy that tells us that the general expansion has to simplify. Let's import another property. Let's import the fact that C is geodesic on the event horizon. So now, basically, we calculate this again, and we make sure that it's equal to kappa C alpha. So we go back to the result. So we go back to the result over here, but this time we multiply by C on the right instead of on the left. So when we calculate this from the expansion, so going up here, so if we multiply on the right, we're going to kill all of those terms over here, because they're all proportional to C, and we're going to kill all of those terms over here because they're also orthogonal to C. Right? So we're going to pick up contributions from B. Well, we don't have an E term anymore, and H. So when we do this calculation, we get minus B times C. And we're going to get minus H A times E alpha A. That has to be equal to this. That means that H has to go away, and B is identified now with kappa, minus kappa. So that means that H is 0, and B is equal to minus kappa. So we can go back up here, we can kill H, and we can replace B by minus kappa. So we're making progress. So that's another property that's taken into account. We can take another property into account. We know that we're talking about a stationary black hole. So we know that the expansion, the shear, and the rotation all vanish for this congruence. And remember what that means. That means that the projected velocity gradient has to vanish. So theta being equal to 0 and theta and omega being equal to 0 means that this tensor over here, which was the projected version of the velocity gradient, has to vanish. So that goes back to the discussion we had a while back about null congruences. So this is the projected velocity gradient, and that's the thing that was decomposed into a trace term, a symmetric trace-free term, and an antisymmetric term. So that gave us the expansion, the shear, and the rotation. If all of those things vanish, this tensor all by itself has to vanish. Now this guy over here basically picks up only the transverse component to the velocity gradient. So if you actually do the calculation of this, it's pretty obvious. This is defined to kill off anything that doesn't point in the transverse direction. So it kills off anything that points along C or N. So all the terms over here that have a C or an N in them end up being killed by the projection. The only thing that survives is this. So the calculation of B tilde, after you do all the projection, only the transverse components survive. That's something that you've explored in a homework assignment. You end up with this expression right here. And if all of that has to be 0, then it means that JAB all by itself has to vanish. So we kill that. So we're making a lot of progress. We still have one important thing. C is a killing vector, which means that the symmetric part of this tensor has to vanish. So that tensor has to be antisymmetric. And if we go back to the general expansion, if we want to kill off the symmetric part, well, we're going to have to kill this. We've already killed that. We've already killed, well, this would implicate the symmetric part of this. This will have to be related to that by a negative sign. And these two guys over here will also have to be related with a negative sign. So this condition guarantees that D will have to be equal to kappa, and F will have to be equal to minus C. And if, sorry, not F, G. G will have to be equal to minus C, and that will guarantee that the whole tensor is antisymmetric. And at this stage, we're done. We have the expansion of our tensor field, and we can't simplify it any further. So the outcome at the end is a much smaller expression. We have a term in kappa, and we have a term in C. Are there questions? So kappa, of course, we recognize that's the quantity we introduced before. C ends up being nu. So we can extract definitions for these guys, or at least expression for these guys that will end up being useful. If I can isolate kappa by multiplying this by n and multiplying this by c. So minus kappa is this vector over here. So I pick up two minus signs when I multiply by n and when I multiply by kappa, by xi. So that's a definition for, kappa, or it's an expression for kappa. And then if I multiply by, from this side, if I multiply by n and multiply by e, let's call it E beta B, then I get CA, I get a minus 1 from here, and I get the induced metric sigma AB from the inner product of the two vectors. Right? So that I can call CB. I can I can lower the index using the induced metric. And that simplifies the notation. So what do I have of all of this? I have a convenient expression for kappa. With a minus sign. And I have a definition for what C has to be. C is related to the derivative of the killing vector in the direction of n and in the direction of the tangent vectors. Transverse vectors. So kappa is basically the derivative of the killing vector in the direction of n and xi, and here it's in the direction of n and the transverse vectors. So we have two ways of characterizing how this tensor field changes as we move around the horizon, and either we pick up components that correspond to kappa, or we pick up components that correspond to C. But basically, we can characterize all of this on the event horizon by basically three quantities, kappa and the two C's, C2 and C3. So all the properties that we imported basically reduce the the number of independent components from something that would be like 16, 4 by 4, to something that is down to 3. So a much smaller set of quantities. All right, so that's just the starting point. So what I'm going to do next is to just start from here and just take derivatives and see what we can find out about all of that. So no mysteries here? Okay. So it's a bit laborious to do all of this, but in the end you end up with something fairly clean and something fairly simple. So and it's going to help in the rest of the calculation. So one thing that I will need, so we've already used the Killing equation in some of what we've done. Killing's equation over here telling us that the gradient field has to be antisymmetric. There's another consequence. There's a consequence of Killing's equation that we're going to need also. That's something that you worked out, I think, in the first homework assignment, that says that the second derivative of a Killing vector field is proportional to the Riemann tensor. So for any Killing vector, this follows as a matter of identity. So the second derivative can be expressed in this way in terms of the Riemann tensor and the Killing vector itself. So that's a property we'll use in addition to all of that stuff. Okay. All right. Let's take a look at the first partial derivative. So the first thing I want to look at is the partial derivative of kappa as we move along an individual generator. So this corresponds to kappa differentiated in the direction of a generator, so that we're moving along the congruence along the Killing direction. And moving along the Killing direction, of course, it has to follow that this is 0, because kappa, presumably like everything else, will satisfy the Killing symmetry, but we can actually prove this in just a few steps. So we have an expression for kappa. We're just going to plug it in and see what we get from all that. So we're going to get, first of all, the derivative of the Killing, the gradient of the Killing vector. So we get our two derivatives here. And that will multiply n alpha c beta. Then we're going to get n differentiated with respect to, I'm missing a c here. I have to put this one in. We're going to get n differentiated. And finally, we're going to get c differentiated, all in the direction of c. Okay, well, we just need to work on this a little bit. For this guy, I'm going to use the Riemann identity, so I'm going to get a Riemann tensor, alpha, beta, mu, nu, that multiplies n alpha, c beta, c mu, c nu. And here we see that it vanishes, because here we have something symmetric in mu and nu. The Riemann tensor is antisymmetric in mu and nu, so the product goes to 0. Over here, what I'm going to do is to take this and that and use the geodesic equation. So for the second term, I'm going to combine this with that, and I'm going to get a kappa c alpha, and alpha differentiated in the direction of mu. And here I'm going to do the same thing over here. I'm going to get minus kappa. I'm going to get c differentiated, multiplying by n, multiplying by c mu. No, sorry. I couldn't do this just yet. I don't have the right combination here, but I can turn this around.
The last one is mu.
Last one should be mu.
Oh, it's mu. Sorry. Okay, so I was right. Okay, so I can do this. So I have kappa, c alpha, beta, and alpha, c beta. Okay. What I can do here, I don't know how n differentiates, but I know how c differentiates. But I know that n alpha, c alpha are equal to -1, which means that if I differentiate, I can transfer a derivative over to the other guy and compensate with a negative sign. So what I can do is to rewrite this as minus c differentiated with respect to mu, leaving this alone. What I'll do here, of course, is to do that again. So here I'm going to have another kappa term arising from this derivative. So at this stage, we're almost done. So from this term over here, we get plus and plus. We get a plus sign. We get well, let me write it in 2 steps. So we get plus kappa, we get C differentiated with N and C. So we're going to use we're going to do the kappa again. Well, in fact, I don't really need to, because for the second term, I have C comma beta and alpha C beta. And, well, it's exactly the same thing, right? I can relabel my indices here, and I get something minus the same thing, so I get 0. So that is the outcome for this derivative, and that means that we have the first part of the proof taken care of. And that one was easy. In fact, well, maybe we didn't even need to do all those calculations, but at least, it follows from the derivation that the derivative along the generator is actually 0. And that's just saying that kappa obeys the Killing symmetry, and there's nothing very surprising about this. All right? So now we're going to do the other one. The other one requires quite a bit more work. Okay, so for the second statement, what we want is the partial derivative of kappa as we go across generators, which means that we take kappa and we differentiate in the direction of the transverse vectors. So the initial steps are pretty similar to what we had before. So we're going to get our Killing vector differentiated twice, multiplied by n, multiplied by c, multiplied by the transverse vector. Then we get c, we get n differentiated, multiplying by c, multiplying by the tangent vector. And then we get the gradient, we get n left alone, and we get c differentiated. So we got that. For the first term, we again use the Riemann identity. So we get Riemann alpha, beta, mu, nu, and we get n, c, e, and c. We get that for the first term. For the second term, well, what do we get? Again, we get a combination that will give us a kappa term. So we get minus kappa. We get a c back. We get an n. And then n is now differentiated in the direction of e. So very similar to what we had before. And for that term, I guess I'm just leaving it alone for now. Okay, here I'm going to use the same trick. Instead of differentiating n, I'm going to flip the derivative over to the xi. I'm going to compensate with a plus sign. So I get the same first term. I get the alternative version of the second term, which is xi differentiated with mu, to which I multiply n, to which I multiply e. And then I'm going to do the same thing over here. No, I don't want to do that. I want to leave that alone, so I'm going to rewrite it as nc differentiated, c differentiated again, times the transverse vector. Okay. This, going back to something we were doing before, if I take my vector c, the velocity gradient, and I multiply it by e, if I go back to this expression over here, I get nothing from here, and I will get a contribution from here that multiplies c, and I get nothing from here. So that combination here will give me a c with an index lowered and a c back. So this gives me sigma AB. Well, I'll just write it as CAC beta, coming from the decomposition we had over there. So I needed that. So I'll use it here. I'll use it there as well. So, yep. So still the same Riemann term. Now we're going to get, over here, we're going to get our C, CA, we're going to get our C back, but it's going to be C alpha that will multiply N alpha. So we get a minus sign from this, so we get a minus kappa CA. So that's the second term, and for the last term, well, now we got a C back. Over here, we get another kappa term. So we're going to get a minus, so we're going to get a kappa from over here, kappa alpha. We get another minus sign. So again, we get a cancellation of the last two terms. But we get something non-zero from the first term. So we're going to have to work on the first term to convince ourselves that, yes, it's zero. So this cancels with that. And at this stage, we have the preliminary statement that says that this partial derivative across generators is not obviously equal to zero. It will end up being equal to zero, but we have more work to do to prove that it will be equal to zero. Right. Any mysterious steps here? Okay. So let me just keep going for another 10 minutes, and then we'll finish it off in the afternoon. Turns out that the essential piece of the Riemann tensor in that equation actually comes from the Ricci tensor. So I'm going to rewrite it in a different form, and I'm going to appeal to the completeness relation to clean this up a little bit. Well, it's not going to look any cleaner. It's going to look more messy for a while, but you'll see where I'm going with that. So let me write down the completeness relation in the following form. So G nu alpha is going to be equal to C nu and alpha minus N nu C alpha plus sigma BC E nu B E alpha C. And what I'm going to do is to take this and that and replace it by the completeness relation. So I'm going to express minus C nu and alpha in terms of the metric. So it's nu alpha. So I'm throwing, I'm keeping this on the right-hand side. I'm going to throw everything else on the left. So that means that I have N nu C alpha, and then minus sigma BC E nu beta E alpha C. I'm going to plug that in. And what I'm going to get, so I'm going to get rid of this, the minus sign in front of the Riemann tensor. And I'm going to plug in, so now I have instead of, so I'm going to replace this n and this c by all of that. And what's left over, we're going to have the c back, and we're going to have the e mu back. So we get all of this. The metric here is acting on the last and first indices of the Riemann tensor that will give me a Ricci tensor with a minus sign. So the first term is going to be minus Ricci with indices beta and mu, and that will multiply C beta E mu. The rest of it, the second term gives me nothing because here I have something antisymmetric in alpha and beta. Here I have something symmetric in alpha and beta, so the second term goes away. And then the last term will give me something non-zero. So in the last term, I'm going to have sigma BC, and I'm going to have R alpha beta mu nu that multiplies, let's see, in order I have C beta, E alpha C, E mu A, E nu B. So let me just rewrite this in a slightly different form. For the second term, I get this. I'm just relabeling the indices. For the second term, what I'm going to do is to switch the pair of indices here so that I can just write it in a slightly, well, cleaner way. So I'm going to write it as mu nu alpha beta. And now the first vector that comes is EA. The second vector that comes is E nu B. Then we have E alpha C and C beta. And that's, well, exactly the same thing as before, but now I've repackaged my Riemann tensor in a slightly different way. So the way this is going to unfold, I'm going to stop here because I think we all look exhausted. The way it's going to unfold is that we're going to prove that the Riemann term is actually zero. This will turn out to be zero. This, again, will not be automatically zero. But we're going to appeal to the Einstein field equations, and we're going to appeal to the dominant energy condition and prove that under those conditions, it is zero. So under the dominant energy condition, we can prove the second statement, but we need to appeal to that dominant energy condition. Otherwise, there's no way of guaranteeing that this component of the Ricci tensor would be zero across the horizon. But with the dominant energy condition incorporated, we'll see that it actually follows. And that is the last step, and after that we have our theorem. So the statement of the theorem then is that, with the fine print inserted, is that we have constancy of the surface gravity on the event horizon under the assumption that we have the dominant energy condition operating on the energy momentum tensor, and we're going to relate the Ricci tensor to the energy momentum tensor by using the Einstein field equations. So there's still a few more steps to go through, but basically it's all going to be about proving that this is zero all by itself, and then making some statements about the first term. All right. So any questions before we break?